All right. Good day, everyone.
Everybody.
I'm so happy everyone's been keeping up with the Python here. I'm looking up because I have a second monitor, so don't think I'm looking down on you. I'm looking up at my screen. Cool. Today it is my distinct pleasure to talk to you about some more Python. Let's do a quick recap. Last time we talked about composite data types, meaning data structures, lists, dictionaries, tuples, all that fun stuff. And today we're going to talk about loops and loops and loops and okay, I'll stop. And we're going to talk about how to run programs in debug mode, and just getting in some more practice with the data structures. Before we start, oh yeah, I saw David already copied the message again into the chat, which is update your version of the repo if you want to follow along in the IPython notebook, or want to be able to scroll on your IPython notebook yourself. I recommend just watching what I do and not trying to code at the same time. It's gonna maybe be a little bit fast. And yeah, let's get going. There's gonna be TAs in the chat again that will help you in case you have issues with anything. If I'm going too fast, please let me know. There is a lot of content in this lecture today. And it's some of my favorite stuff to talk about in Python. Oh, before we start, I should probably put down the blinds a little bit because I'm going to get blinded by the end of this lecture. 1 second. There we go, much better. All right, everyone can hear me?
Yeah, that works.
Okie dokie, perfect, cool. All right, so today we're talking about iteration. A lot of people were already kind of jumping the gun last time and asking, well, how do I do this for everything, for every key in the dictionary, or how do I do this thing for every item in a list? That's exactly what we're going to talk about today. So iteration is commonly used to do something for each item in a sequence. So let's say, for example, we have a list of patients. We need to assign them to treatment groups for a clinical trial, excuse me. Or we need to repeat something n times, like let's say we have a snooze button and it has to snooze 5 times for a minute, for example. And then the last kind of way we're going to go over is our loops or iteration patterns, where we can repeat something as long as some condition is true or false. This is useful when we don't know how many times we want to do something. For example, especially important when we have a statistical model that we want to refine some parameters on, and we want to say, okay, we want our model to fit this well on the data. So keep refining the model until it fits this well on the data. So let's get right into it. So the simplest way to iterate in Python is to use a for loop. For is a compound statement, which we use to apply some kind of logic to each item in any iterable. An iterable, as kind of a tautologic definition, is anything that you can write a for loop for. So any sequential type, anything where you think, okay, this makes sense, that has, it's an object that has multiple separate items in it, kind of in a sequence. So for examples of that we went over already, are strings, lists, dictionaries. An example of a basic type that you can't iterate over is, for example, an integer, right? It's just a single number. There's not really much to iterate over there, but we'll learn later how we can iterate n times, right? We can say, okay, we want this loop to run 5 times, for example. We'll learn how to do that later. So the basic structure for a for loop is for every item, for each item in an iterable, and we don't have to write the each, for item in iterable, do basically something, do some action. And you see here we have this indent. This tells Python which part of which part of the code belongs to the loop. If we remove this indent, Python thinks this is not part of the loop anymore. And we'll get later also into how we can distinguish multiple loops inside of each other. So for example, let's say we have a list of genes. We want to translate each gene. The Python code for that would look something like this. And so let's just get right into it. Let's say we have a list of vowels and we want to print each of the vowels in this list. So we say for vowel in vowels, print vowel, and I've already kind of neatly copied that in here, right? And so we can just execute that here, and Jupyter loads, nice, and you can see that basically it goes through the list and it prints each of these vowels. Now there's a couple of things here going on, right? First of all, is this this variable here, right? This is our iteration variable, vowel. So Python actually, under the hood, picks each of these items out of this list, and for one iteration of the loop, assigns the value of that item to vowel. And you can see here after the fact, I have this print statement here where I print and this, you can see this is outside of the loop. This is not part of the loop anymore because it's not indented. And I'm printing the value of vowel here. You can see that the last vowel in the loop was U, and then even after the loop has ended, vowel is still equal to U. So this is something to keep in mind. Naming this iteration variable something that you haven't used elsewhere in your code so that it doesn't overwrite that other variable from other parts of your code. So it seems obvious that this is super useful to me, but just to drive the point home, if we wanted to do this same loop without the same code without a for loop, we would have to write out each of these vowels individually, right? We have to say, well, vowel equals vowel 0, vowels 0, and then print the vowel, and then next vowel equals vowels 1, and then print the vowel. And so you can see that we basically save a lot of code by using this loop here instead of writing this out individually. Also, it makes our code more flexible, right? Because if we make vowels bigger, now we don't have to, if you make the list bigger, we don't have to write an extra loop. The loop will just run the same way. It doesn't matter if this list is 10 vowels long or 15 vowels long. Well, it just happens there's only 5 vowels in the English alphabet anyways. All right. Now, a practical example of this would be to find, for example, the summation and the product of a list of numbers, right? So let's say we have a numbers list of 1, 2, 3, and 4, and we want to find the sum of these numbers. Now, how do we go about writing a loop for that? Generally, the way we construct a loop for a problem like this is we first initialize some variables before our loop starts. Then we apply some computation for each item in the loop body, right, which is the part that's indented, and in which we're maybe changing some variables. And then after the loop terminates, we can use the result of that computation. So here we have a loop written that computes both the product and the sum for us. And let me just copy and paste that in here. real quick. Because here we get syntax highlighting, so that's a bit nicer so you can see what's going on. So we're going to import math here for the power function. And we're going to initialize our list here real quick. And we're going to make a new variable that we call sum underscore and initialize that to 0, right? So at the beginning, our sum is 0. And we'll also initialize our product at 1. And then for each num in our num list, we'll add num to our sum variable. So we're summing up, and we will multiply our prod variable, which is initialized at 1, right, with our num, so that we get basically the product of all these numbers. And then after the fact, we can just use, we can just print these variables. So this would be the equivalent of us using this summation or this product, right? So let's run that code real quick. Oh, and inconsistent use of tabs and spaces in indentation. All right. Let's see what's going on here. Zip. And okay. So this is a master class in how to mess up formatting. I think this is a common problem with copying this code from VS Code. I've done that for most of the other cells before, but this one was so simple that I didn't think to do that. Okay, unexpected end of file while parsing. So that means there is something is open here, some parentheses is open here, and that's this parentheses here. Name prod is not defined. That is correct because we didn't give it an underscore. And there we go. Only took like 5 tries. All right. And okay, so we see that the loop works. We basically summed these together. 1 + 2 is 3, + 3 is 6, + 4 is 10. So our sum is 10. And our prod is 24, which is 1 × 2 is 2, × 3 is 6, × 4 is 24. Perfect. So our product is also correct. And then we can use that in more creative ways, right? We can look at oh my God, so many tooltips. We can look at the average by just dividing the sum by the number of items in our list. For that, we can use the Len function. The Len function lets us determine the length of a sequential type. So for example, for a list, it tells us how many items there are in the list. Really, every kind of object can define on its own what len means. So really just len asks the object to tell you what its length is. So if you ever use len on something and it's kind of a surprising result, just remember it's on the duty of the object to tell len what the length should be. And here we're using the math.power function, which is basically x to the power of y. So product of, so if we take the product to the power of 1 over the length of our list, then we get this GM here. Okay, so this is the general way we construct loops, right? We initialize a variable, or in this case, 2 variables. Then we loop over some kind of sequential type. This is our iteration variable, right? These are our what we call our accumulator variables that basically accumulate some kind of computation for each item in our num list. And then after the fact, we can use the results of that computation. We can use the fruits of our labor. All right. I'll quickly drink some water because I am a raisin. All right. And let's walk through that real quick basically one by one. In the beginning, this is before the loop. We're initializing, right? We're saying sum is equal to 0 and prod is equal to 1, and then the for loop begins, and we add the first number in our list is 1, so sum is now 1, prod is 1 times 1, which is 1, and then the next iteration of the loop begins. Num is 2, so 1 plus 2 is 3, and prod, well, 1 times 2 is 2, and so forth, and then we end up with our for loop completed. The second type of pattern that I want to talk about, and I need to kind of pace myself a little bit because we got some stuff to cover here today, is using the range function. This lets us basically complete the loop n times. So last time we talked about how you can use lists, right, to kind of store sequences of numbers. If we just want a certain range of numbers, in this case for a for loop, then it's usually better to use the range function. It has a lot more flexibility. We can access the elements by index and reference rather than instead of direct access. And so basically a range object doesn't have to compute, like a list stores all its elements in memory at one time. A range function is more like a math object that you can ask it basically which part of the number sequence you want, and it'll under the hood compute that part of the sequence for you. So it's a lot more useful than lists if you're dealing with lots of numbers. And this range function is built in, and it returns what we call a range object. So if we say, actually, let's type that in here, right? Let's say x equals a range of 10, and let's give the type x. It's a range object. It doesn't give us a list. And very old versions of Python, these used to return lists. This is no longer the case. And this is what we call a lazy object. So if I just let it print x here, it'll just tell me, well, this is a range from 0 to 10. That's all it is. It doesn't give me the individual numbers in the list, in the range. So to get those, I have to force, for example, list to force build the entire range. And so here we see another example. So in the range function, we tell it the start, the stop, and then we tell it the step, meaning here, for example, we're using every third item. If we deleted that, it would just give us all the items from 0 to 10. Again, the stop is not included, much like when we were doing the slicing and indexing last lecture. So from 0 to 10 means all numbers from 0 to 10 except 10. So this can be useful if you need to iterate over, well, different ranges of numbers. And then you don't have to do some weird construction of a list or something. The nice thing about this is that we can natively iterate over this range function. So here's another example where we use that. It's maybe a bit convoluted, I would say, where we say, well, for each index in the range of the length of this list, we're going to print the index, and then we're going to fetch this item at that index from that list. This can be useful if you have a lot of different lists that have the same length, and we'll see an example here just in a bit. In this case, this is maybe a little bit of a misuse of the range function. I would probably write this differently. I would write this, I would use another magic function from the Python arsenal, which is called enumerate. And that lets us that lets us take basically one item at a time out of an iterable, and it additionally gives us the index of that item. So this gives us the same thing, where basically this enumerate clause, what this returns us is it gives us always, for each item, it gives us a tuple of the index and the item in this iterable. And you see here, I'm not using one iteration variable, I'm using two iteration variables here in this for loop. This is a concept in Python known as sequence unpacking. Really what the for loop is just doing is it's using an equal sign, right? It's saying, let's say the first, what is the first tuple that we should get? The first tuple that we should get is 0 and A, right? This is a tuple. This is our first tuple. And basically the loop goes through this enumerate, these tuples we get from enumerate, and it'll say, well, index, comma, item equals to 0, comma, A. And so we can print again, index and item here real quick. And so basically this unpacking, you can use this anytime you do what we call assignment, right? Every time you have a single equal sign, that's called an assignment. And that's what's happening under the hood in this for loop, right? Very, very useful in this case, for example, when you use enumerate, you don't have to write something, you don't have to take the whole tuple at once. You can just, and then assign, and then pick it apart manually. You can just do that in the for loop definition here. All right, so that's just a neat little trick we can do here. But there are cases where it's useful to use the range function to just generate a bunch of indices. And namely here, and I'm already grueling this because there's probably gonna be indentation errors again. Let's see. Nope, no indentation errors this time because, yep, these are all good. Nice. So here what we're trying to do is we're trying to create the dot product of two vectors. So we'll have our vector 1 and our vector 2. And for those who need a little bit of a refresher in math, the dot product is basically you line up two vectors and then you multiply the items that look across from each other. So in this case, well, 1 times 5, 2 times 6, 7 times 3, 4 times 8. And then you add all of those results together, and that's the dot product of two vectors. So we'll initialize this dot product at 0.0 here. This is a stylistic choice here. We're using a float. And then for each index in the range of the length of this first vector, because we know these two vectors have to have the same length if we're supposed to do a dot product with them. And then we basically add to our dot variable, right? Again, we initialize this dot variable at 0, and then we're gonna add to it the product of the index of this index in vector 1 times what we find at this index in vector 2, right? And then we just have another print statement here. Cool. Another kind of classic example, I think that people often like to bring up in these courses, mostly because a lot of, I think, computer scientists are very math affine, is the Fibonacci numbers. So the Fibonacci sequence is a sequence of numbers that starts with 1, 1, and then each subsequent number in the sequence is the sum of the previous 2. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 2 plus 3, and then it's 8, 13, 24, 35. Oh no, don't remember the ones beyond that, but I don't have to because I can just write code to do it. And so here, just to drive this kind of how we build up loops concept. Again, same thing. We have some variables that we start at the start. We say, okay, our list Z begins with the name with 1 and with 2 times the number 1. This is just a fancy way of making a list that has 1 comma 1 in it. And then for every index in the range of 2 to n, right? Because we want to have 10, we want to have 10 Fibonacci numbers here. We're going to intermittently store these numbers in a variable we call next. This is actually not a good name because next, you see next light up blue here. If something lights up blue in your VS Code in Python, that means this is some kind of built-in parameter. So we'll just add an underscore to this here, just so we don't delete our next variable, our next built-in function for now. And then basically we'll intermittently store in this next underscore variable Z at the index -1 and Z at the index -2, add it together, and let's see what that gives us. So basically that gives us the, oh yeah, it was 34. I was right. Huh. Interesting. Still got it. And you can see basically that this is a way that this time we didn't iterate over some kind of list that we had pre-made. Instead, what we did was we iterated over some number range and then cumulatively built up a larger list by basically always computing some kind of value, some kind of new value based on existing values. All right. Now I've showed you upwards a little bit more upwards how we can make our own version of sum and prod. There are built-in functions for many of these tools in Python, and so most of the time it's better to use the built-in function. So whenever you do something in Python where you're like, well, this must come up a lot. Like a lot of people must be running into this issue sometimes when programming, right? Or needing this tool. That probably means it's somewhere in the Python library and you just haven't found it yet. And so, for example, there is a dedicated sum function that we can use to, and of course, we have an invalid character in an identifier. Oh yeah, that's because these are not proper quotes. There we go, okay. For some reason for me, it keeps scrolling down a little bit. All right, I hope everyone's still awake because this party is about to get started. We're about to go into nested loops. But just to go over this again real quick, right? This is our loop from beforehand, how we made our own kind of sum, and we didn't have to do that. There's a dedicated function for that. So also when you're doing homeworks or kind of take-home assignments, oftentimes like a couple minutes of looking through Python documentation or Googling Python questions will save you a lot of time coding. So keep that in mind. A lot of very common problems will have been solved. And that's kind of a theme that's going to come more and more through this lecture. All right, it's about to get slightly more complicated. So now we've talked about loops, and right, we said, well, loops are defined by this indentation, right? This is how we know what's happening inside and outside of the loop. So now you can say, well, we can put another loop inside the loop, right? And that's exactly right. That's exactly what we're going to do. And so here we've prepared a little bit of an example for j in range 5. So numbers from 0 to 4, basically. We're going to print this j. And then for every time this loop iterates, we're going to also, within that loop, iterate over this I in range 2, which is going to be the numbers 0 and 1. And we're going to print that I, right? And so this inner loop will be repeated for each iteration of the outer loop. And we can calculate the number of times print will be called by saying, well, this outer loop has a print statement, and this outer loop is going to run 5 times. And the inner loop is going to be called 5 times, and it's going to be called, it's going to iterate twice each time it's called. And that means we're going to have 5 times 2 print statements from this inner loop. So that leaves us at that leaves us at a whopping total of 15 iterations. So let's try that out real quick. And so basically the way that this looks is, well, here's the outer loop, and then the inner loop runs twice, and then the outer loop iterates again, and then the inner loop runs twice, and the outer loop iterates again, and then the inner loop runs twice. Now we're going to try our hand at a little bit of a practically worked example. Kind of algorithm that's, I think, very frequently used. Well, not this implementation, not the bubble sort, but sorting algorithms are everywhere. We need to use them. We use them a lot, even if we're not intentionally using them oh so often. A lot of bigger algorithms use sorting algorithms. This bubble sort algorithm, however, is more meant for teaching. It's not super efficient, but it's relatively easy to implement. And so we're going to show you how to implement this with a couple of for loops. So what's the challenge? We have a list of unsorted numbers, and we want to sort that list. And so we're going to and this is pseudocode, this is not Python. Pseudocode is basically just, you write it out in common words, without thinking too much about the kind of language specific implementation, and then you can go into your language, for example, Python, and write it out. So here we're going to have our list of unsorted numbers, and we're going to declare n is the length of our list, and then we're going to start from 0 to n minus 1, right? So basically for each index in the list, we're going to run this outer loop, and then we're going to run this inner loop for each index in the list. And what we're going to do in this inner loop is, if the number at a of I plus 1 is smaller than the number of a at I, we're going to swap a at I plus 1 and I. And it's not super trivial to think about why that would end up in a sorted array. And so I have a little GIF here that I can show you folks. Let's see if that works. Okay, so here we have our list of unsorted numbers. They're basically visualized here as like long bars. And what you can see is basically this red cursor is our loop iteration. It basically keeps iterating through the entire list and always swapping out adjacent numbers if one of them is larger than the other, right? And so what you can see is basically these small, each pass through the list, the next smaller number, the next smallest number basically finds its right location in the list here. Because, and let's go back to the algorithm real quick again. Basically, we're always looking at two adjacent numbers. In our case, it's a bit different. In our case, the bigger numbers are going to go to the right side. But that doesn't matter. You can go it either way. We're always looking at two adjacent numbers, and if they're in the wrong order, in this case, the larger one is gonna take its rightful place to the right, and then we're gonna do this comparison again with the next two numbers, and if the left number is again larger than the right one, we're gonna put it to the right, and so on, and so on, and so on. And so if we do that whole pass to the list, to our whole unsorted list once, the largest number is always going to find, we're always going to find that this way the largest number made its way all the way to the end of the list. About this algorithm, and I know this was a mouthful, and don't worry if you didn't understand everything completely here. That's not really the point. Even though this was already a mouthful, this is one of the simpler sorting algorithms. It's highly inefficient. And here we're going to talk about a little kind of more technical tidbit real quick. We call this, we quickly tell each other how efficient these algorithms are by this, what's called this big O notation. And this one has an O of n squared. Big O just means a measure of the algorithm's performance. So basically, n is what we call the problem size. In this case, n is the length of our list of unsorted numbers. And because we have our outer loop, which iterates n times, right, from 0 to n minus 1, that's n times. And then we have an inner loop that also iterates n times. So basically, these two loops are going to iterate n squared times. And now you may say, well, but there's also a cost to this comparison, and then there's a cost to this swapping. When we're doing this big O notation, we're always looking for the factor in the program that scales the most quickly with increasing the problem size. And so in this case, yes, there may be some kind of linear effects here and whatnot, but the thing in this algorithm that's going to scale the most quickly is with n is these two loops. And here are a bunch of different kind of common big O's. An O of 1 is what we call constant time. So the number of elements does not change the performance of the algorithm. Fun fact, and we'll talk about this a bit later, looking up a value in a dictionary, looking up a key in a dictionary in Python has an O of 1. So if you're interested in, that's kind of counterintuitive, right? You'd think, well, if you have more keys in your dictionary, it should take longer to look up, right? So if that keeps you curious, you should look that up for the lecture. And then there is, for example, O log of n, which is log time. So the algorithm, this is always going to be less than n. So this algorithm never has to look at all of the elements. This is a great place to be. O of n is what we call n time, or many people will call it linear time. So this algorithm will look at each element at least once in the worst case. And then our O of n squared is somewhere here in the middle between these. And then O of 2 to the n is what we call exponential time. You never want an algorithm with a performance like this. I actually just recently ran into an algorithm that had this performance, but this was like, it was part of a package that I was using, and they were kind of downplaying it in the documentation, and I ended up kind of graphing out the performance and figuring out that way that it was in this space. And they said slight slowdown. This is not slight slowdown. This scales really quickly. So if you have an algorithm that scales with of 2 to the n, you either can use it on very small data sets only, or you have to think about a better algorithm. In our case, O of n squared the algorithm will evaluate each number basically against each other number. This is how you can think about it. Basically, it's going to make a full pass through the list, which is going to be, well, n comparisons for each number of items in the list. So that's why we're at O n squared. And this is, again, due to the nested loops that are both iterating n times, and because they're nested, that means their n's are multiplied with each other. And why am I talking so much about this? This is something important to think about when you're running analysis code and it doesn't complete immediately, or it doesn't complete in a time that you think would be reasonable. I usually don't think about this that much when I write analysis code, because most of my analysis code runs in linear time, basically. But sometimes it doesn't. So an example would be, I have a couple of different cancer samples, and I want to compare each cancer sample against each cancer sample. Well, that's an O of n squared, right? I have to compare n cancer samples to n cancer samples. So how many samples do I have, right? And if I just have 50, 60 samples, that's not that bad. But what if I want to compare each gene against each gene? That starts growing really quickly. So I have to think about, well, will this run on my laptop? Will this run in a reasonable time? Nested loops are an easy way to figure out that you have something like O of n squared. Usually when I have a nested loop, this can often be a warning sign. But it's not always that obvious when you're looking at code where the loops are. There's kind of smart ways of hiding those from the code. And again, it's okay to write code that's not perfectly efficient. Only optimize when you need to. But when you suspect a code is running too long, try it out on a smaller data set, test it out on a smaller data set. See if it runs, see how quickly it runs. And if it takes longer than you think, run it on a slightly larger data set, see how it scales. All right, wow, that was a lot of explanation for big O. Again, it sounds very scary. You don't have to be a mega expert in it. It just helps to have heard about it once, at least. So have it in the back of your mind when your code runs too long. All right, so let's make some random numbers. So we're gonna import the random module, and we're going to make 15 random numbers at a range of from 0 to 50, well, 0 to 49, basically. So here are some random numbers. Let's sort these. Let's see first if that worked. Okay, so here we have a sorted list of numbers. So our algorithm worked. Again, this is our implementation of the algorithm we talked about before. We first have our list, a random list of numbers. Then we're going to set n to the length of the number list. And then for j in range of n minus 1, and for I in range of n minus 1, we are going to swap these adjacent, we're going to swap these adjacent elements if the one on the left is larger than the one on the right. basically. And the way we do that is we first check if if our number on the right side is smaller than our number on the left side. And if that is the case, what we're going to do is we're going to create a temporary variable here, and we're going to say number underscore list of I plus 1 is our temporary variable. And so now we're going to assign the index of number list of I to I plus 1 because we stored I plus 1 in our temporary variable. And now we have now we can assign our temporary variable basically back to I, and we've successfully swapped two numbers, right? There's one more way, kind of trickier way to do this, which uses what I was talking about a little bit earlier, which is called the sequence unpacking. But this is a bit more confusing, which is why we didn't opt for the implementation that way. Basically, what we can do is we can swap the numbers this way, because the way that assignment works, this equals thing works, is this part is going to be evaluated first, this side. And then it's going to be a tuple, and it's going to go through this equal sign, and then it's going to be assigned to these two. So this would be kind of a quicker way without a temporary variable, and this works just as well. This is just kind of a neat trick, you know, you're gonna impress your PI. All right, let's visualize this sorting process one more time. You don't have to worry about the code here. You can look at this later. This is just gonna give us a kind of a pretty visualization of what's going on in our loop. So here we're deliberately starting with a list that's basically in the reverse orientation, right? Which is usually what we call the worst case scenario. Excuse me, too much pizza. We're going to start from this reverse sorted list, right? We want this whole list to be in the exact opposite orientation. We want all the larger numbers to be on the right side and the small numbers to be on the left side. And so this is first iteration of the outer loop, basically. And our first check is, well, is 5 and 4, is 5 larger than 4? Yeah, it is. So let's swap these two. And then we check, is 5 larger than 3? Yeah, it is. So let's swap these two. And then we check, is 5 larger than 2? Yeah, it is. Let's swap these two. And then is 5 larger than 1? Heck yeah, let's swap these two. And now you can see what this is called bubble sort, because the larger numbers basically tend to bubble to the top to the list really quickly, right? In one iteration, they just find their correct place in the list. And then our second iteration, well, now the number at the bottom of the list is a 4. Well, that's larger than 3, so let's swap. Well, 4 is larger than 2, let's swap. Well, 4 is larger than 1, let's swap. Well, 4 is smaller than 5, so let's keep it. And so you can see how this loop, would finish to give us our sorted list. All right, here are some practice problems that you can try at home. We're not going to have time to go over each of these because we have a ton of content to still go through, and we only have like 40 minutes left. A quick check, are people still keeping up? Are people overwhelmed? What are people kind of feeling like? Because I haven't been able to see chat. It's not giving me any, oh my God, there's a lot of messages here. I'm so sorry. It didn't give me any notifications. All right, people are still in high spirits. Again, if you have questions towards anything, I'll be in the Stack Overflow later. Okay, looks like everyone's able to follow, I'm going to resist the temptation and speed up significantly. Again, these are all practice problems. They're all in the notebook. They start out relatively simple and then become progressively more difficult. All right, here's another example, and we'll walk through this one together. Another common thing we do when we loop is we have some kind of, a long list of numbers or something like that. We just want to, aggregate some statistic or just summarize something about this long list of numbers. And really, most of the time, it's numbers. So for example, here we could say, well, we want to count the number of times each number appears in this list. Excuse me. And maybe we want to order them according to frequency, but that's maybe for later. So how do we go about this? Well, does anybody have an idea of how we can keep track of how many times we've seen a number? Like, what kind of data structure would be good for keeping track of how many counts we have for each number? For some reason, it won't let me show my, oh, where is my chat? Show me my chat. Okay. Cool. Does anybody have an idea about what data structure we can use to keep counts keep track of counts of different numbers, right? Let's say, oh yeah, there's the first one, a dictionary. That's exactly right. That's exactly what we'll be using. And so here we have our list of numbers. We're going to import pretty print here, and so we can get some prettier printing down the line. We're going to initialize an empty dictionary here. And then for each number in our numbers list, we're going to say if that number is in our counts dictionary already, we're going to say, well, the counts of number equals to counts of number plus 1, right? Because we're basically counting up how often we see this number. Else, if we haven't seen this number before, so it's not in our counts dictionary already, we're just going to initialize it at 1. And, oh, I hear somebody who is unmuted themselves. What is going on there? Okay. Real quick. Okay, so we have our counts. So that worked. Okay, so we have, again, we've gone over our numbers. If the number was in counts, we added 1 to it. If it wasn't in counts already, we initialized its value at 1. And pretty print orders our dictionary by the keys, and so that's why they're in this order for us here. And we see, well, for example, this seems to be the most common number. 1 seems to be the most common number. There is another way we can do this that's maybe a bit more clever, where dictionaries have this get method that basically says, get the value of this key. And if you can't find the key, give us some default value. Well, we'll get 0 as a default value here. And so this way we don't have to make this if-else check. So that saves us a little bit of code. Oftentimes writing less code is a good idea, because the less code you write, the less you have to read. Not always though. Sometimes it's better to take the longer route. But in this case, again, this gives us the same result, so that works. And now you may say, well, wouldn't it be nice to have a dictionary where just all the values are some kind of default value, and then if we haven't found the key yet, it'll just initialize it for us automatically at some value? Well, you're in luck. There is the collections module, which is one of probably the best parts of the standard library. And we're going to have a link for that at the end of this lecture. Definitely take a look at that. And it has an object called the default dict. So what we're going to do here is we're going to initialize our counts dictionary as a default dict. And it says here is a dict with a default factory. So the default factory is called without arguments, produce a new value when a key is not present. Oh, I see something flash up in the chat. Let's see. Oh yeah, nice. David already printed the list to the, oh, but that's the Python 2. That's the Python 2 link. Don't use Python 2 if you don't have to. It's deprecated. All right, back to this. Basically, what's happening is if this default dict hasn't seen a key yet and we're trying to access it, it initializes it at 0 for us. And then that way we don't have to do this get nonsense. We don't have to make any if checks. We just say, well, we want to add up the counts. We would just want to add 1 to the count of a number. And if the number wasn't in the dictionary yet, it's just going to be added as 0. So this is going to look a little bit different from a dictionary because it's going to tell us, well, this is a default dict, but it acts, you know, if it looks like a duck and quacks like a duck, right? It acts like a dictionary in pretty much every other instance. So it's very useful. So here's a quick demonstration of how this default dict works, right? We're initializing here at the top, then we're going to print the value of x. X is an empty default dict in this case. And then we're going to print the value of x of 1, and it's going to tell us that that is a 0. And that's because it initializes every value that we look for at 0, right? We hadn't defined that beforehand. Now, if we print x again, we see, oh, there's a key value pair in here, which is 1, which is the key we were looking for, and 0. So as soon as we look up a key, it assigns the default value to it. We don't have to assign to it, we just have to look it up, right? So important, which is important. All right. And it turns out in the collections module, there's an even more streamlined solution to this problem. Let's copy our numbers list again real quick. And that's what's called counter. Yeah. You'd think that you would run into the problem of counting things relatively frequently, and in fact you do. And that's why the collections module comes with a dedicated counter. And that does basically exactly the same thing that the previous ones did as well. And yeah, so if you need to count things, use counter. Don't come up with your own kind of sneaky way of doing it. Although default dicts are great, if there's a dedicated solution for it in the standard library, it's probably best to use it. And counter works on any kind of iterable, right? Not just the list of numbers. So for example, we can use it here to count the numbers of A's, G's, C's, and T's in a DNA sequence. Thinking about, for example, GC ratios, right? When you're designing primers for a PCR reaction. And for anybody who that didn't sound like anything to, that's okay. That's just for all the molecular biologists out there. But yeah, counter works on any kind of iterable. So very useful tool. We have one more kind of common pattern to go through, which is aggregation, which is similar to, but slightly more involved than the example we had above, right? And so here we're interested in the genetic code. And the genetic code gives a mapping from nucleotide triplets, which there are 64 of, right? 4 times 4 is 16 times 4 is 64, to amino acids, of which are only 20. So there's some redundancy in the code. And there's lots of biological reasons for why that's good. Oopsie. But what we want to do here is we want to know which triplets code for phenylalanine. Excuse me. And you can think about two ways we can do this, right? We can say, well, we'll just iterate through our genetic code dict once, and once for each query, and assemble the results. So for example, when we're looking for phenylalanine, we'll only care for the keys that have the phi in it, right? But oftentimes it's good to look ahead a little bit for what you might need. And so the better solution here would be to kind of pre-compute the results for the entire dictionary here, right? So we're basically going to invert this dictionary. We're going to say, well, we're going to pre-compute the mapping from amino acids to nucleotide triplets. So what's the best way of doing that? Out of the tools we've just learned, right? We've learned about a counter, we've learned about dictionaries, we've learned about default dict, and for loops, and nested for loops. What data structure are we probably going to want to use to store this new mapping from amino acids to nucleotide triplets? Anybody got any idea? I'll give you a hint. Well, we're using a default dict. Initializes keys as amino acids. Interesting. Unfortunately, there's no amino acid type, but I'll give you a hint. One of the problems we're having here is that some of these keys, right, like for example, phenylalanine, have multiple they have multiple codons that code for them. So the keys in our dictionary should be the amino acids, yes, but what should how do we make sure we can get the values right? Because for some of them we're just going to need one value, and for some of them we're going to need to put in multiple triplets. Yeah, exactly. So the value of the dict needs to be a list rather than a string. That's exactly right. And so what we're going to do here is we are going to initialize our genetic code. Then we're going to say, well, this is our amino acid codon map. And then for each codon and amino acid in our genetic code.items, .items gives us basically the key value pairs one at a time for the dictionary. Because if we normally iterate through a dictionary natively, it'll just give us the keys. So if we want keys and values, which we want in this case, we want the codons and the amino acids, we're going to use items. So for each codon and amino acid, if that amino acid is in our amino acid codon map, we're going to say amino acid codon map of this amino acid dot append this codon, and else if this amino acid is not in our codon map yet, we're going to initialize it as a list of this first codon. And voila. And it turns out tryptophan has only a single codon that codes for it, which is actually really relevant biologically. So if you're interested in that, lots of literature on that. Now, of course, there's a clever solution, which is using the default dict, right? Because we don't just have to use the default dict with int, we can also tell it to construct the list by default. And that's exactly what we'll do. So we're saving ourselves, again, this whole, you've seen this pattern before of checking if something is in this dictionary again. That usually should tell you, well, I probably want a default dict if I'm always doing the same thing. And all the values should be the same kind of type anyways. Yep. So we're going to use a default dict, and it works just as well, because then we can just say, well, in our default dict AA codon map of this amino acid, we're going to just call the append function of, because this is going to return us the list, that's the value for this key, and that list has the append function. So we can kind of chain operations here. In general, every function in Python, this is what's called a function call, right? If you have some kind of word, and then you have and then you have two parentheses after, that's called a function call. Every function call in Python returns something. Many of them return none. So print, for example, doesn't have any return value. But in this case, and so for example, this also doesn't return anything. But if this returned, for example, another list, we could chain another operation after here. This is not always best for the most readable code, but just so you know, each of these statements, you don't have to always declare like new variable or what have you, if you just want to do a couple of operations in a row. Cool. So we found another good way to use default dict. And here's again kind of the intuition for how that default dict worked here, right? So we initialized it as an empty default dict of class list. Then we look up this a value, and now all of a sudden the a value is in our default dict. And then we can say, well, we're going to append 10 to the value of b. So first it generates an empty list for b, and then it appends 10 to it. And we can call that again and again, and so forth. Cool. Next up, we're going to talk a little bit about, it's called control flow, right? Which we already talked a little bit about in the previous lecture, or in the lecture before that, actually, I think, where, if-else statements can kind of let you determine which path your program should take, right? And so we have two more control flow elements that are dedicated to loops, right? And so those are the break keyword, which tells our code to stop the current loop from running any further, meaning it breaks out of the loop. For example, in this case, we have, actually, let's see, no, I didn't copy and paste this before. Let's see. We have a list of numbers here, 1, 3, 5, 6, 9, and 10. And for a number in numbers, if the number is divisible by 2, right, modulo division by 2 gives us the remainder of that division. And then if that remainder is 0, then it's an even number. Break the loop. Else, oh, there's no else statement. And then we just print the number in the loop as well. And so you can see, well, it goes 1, 3, 5, and then it hits 6, and the loop breaks. It doesn't even print 6 anymore, because at that point, the printing is part of the loop, so it's just broken out of the loop, right? And there's another keyword that's called the continue keyword. And this does the same thing. This is a similar thing to the break keyword, but it just tells us to skip over the current iteration of the for loop. So of the current loop, sorry, this works with for and while loops. We'll talk about while loops in a little bit. So if I change this to continue, and let's call this continue, you can see that basically the 6 and the 10 just got skipped here, right? So when we hit the continue statement, the print skipped, and we just go back to here. And I'll show that really quickly in this break example. And zip, zip, zip. I have to find the right keys. Oh, sorry. Oopsie. Oh, yeah. We're going to try our hand at debugging. And we're going to set a breakpoint here, right? So we can set these debugging breakpoints in Visual Studio Code. What I did is I just opened this breakx.py file, and then I'm going to press F5 here, which puts me in debug mode. I'm going to say, well, I want to debug the currently active Python file. So let's give that a go. That's going to open the terminal for me. And zip, and we're at the break statement. So let me quickly resize this here so you guys can see the code. Sorry, you folks, you couldn't see the code, but also the terminal. So we're here in the terminal, we're in debug mode, and we're right here where it says for character in letters. And sorry, this is a slightly different problem. Oof, so many tooltips. It's hard to see. Sorry about that. Oh, yeah. 1 second there. Okay. So here what we want to do is we want to print basically each combination of characters and letters. We have this letters list and this numbers list. And so first we're going to iterate over characters and letters, and then we're going to iterate every time for each character, we're going to also iterate over each number and numbers. And then if the number is divisible by 2, we're going to break. And then after that, we're going to print the character number. So let's see how that goes forward. So we're going to go to the next statement. Okay. And we're going to go to, so now we can actually check, sorry. Oh, no, sorry. And now we can actually go one further, and we're going to check. So we can see here our local variable characters. Our character is A, right? Letters is still the same. Numbers is still the same. Our number is 5, which you can see right here. Is our first number. And then we're going to check here, is this number divisible by 2 or not? And it is not, so we're going to print it, and it's printed out. And then we're going back to this again. And now we can skip ahead, and you can see that this number variable changed, right? Because we're in the next iteration of the loop, and so on and so on. And 9 is again not divisible by 2, so it's again printed. And then now we're coming up on our number is now 10. 10 is divisible by 2, and so we reach a breakpoint. And so the loop breaks, and we go to the next character. And then we can just click forward and keep continuing this, basically. This debug mode is another kind of useful tool to investigate what is going on in your code. If you ever have any issues in your code, you can just set these breakpoints and then go one iteration at a time. So that can be quite useful. And you can look at your local variables here on the side and globals as well. So that can be really useful, another really useful tool in your build. All right, let's stop this for now. Let's go back to the lecture. Let's close this and let's exit out of this terminal. Let's see, let's exit out of this as well. And we're back. Okay, so we're talking about, oh, I forgot to show you the continue keyword in action. You can imagine how that goes. In that case, it wouldn't break this an inner loop. It would just skip to the next iteration of the loop. Excuse me. I have a heater right next to me. The air is formidably dry. All right. Oh yeah, this is what I just showed you basically. That these break and continue keywords, they work on the immediate and closing for loop. So if you call break in a nested loop, it's only going to break the loop in which you're calling the break. It's not going to break all loops, you know, that this loop is in. It's going to just break the part of the nesting level of the loop that you're in. And same for the continuous statement. All right, let's skip over that. Here is a nugget for you. The else statement, actually a lot of, I think, seasoned Python programmers will not know this, but the for loop also has an else statement. And this is exactly relevant for this kind of code because this else statement lets us execute code if a for loop completed without hitting a break statement. So this is sometimes useful when we have an if condition inside our loop like we had here, which depends on our loop variable and can break the loop. So here we have some fruit baskets, right? And we want to know which of these baskets have apples in them. But also we want to print the items in the fruit baskets if they don't have apples in them. And so we're going to say, well, these are our fruit baskets. Notice the last basket has apples in it. And then for each basket in our fruit baskets, we're going to print which fruits are in the baskets. And then we're going to, for each of the items in the baskets, if the item is an apple, we're going to print, how do you like them apples? And we're going to break this inner for loop, and we're going to go on to the next basket. Else, if that item is not an apple, we're just going to, else if that iteration of this loop had no apples, else if this for loop concluded without any breaks, we're going to say, well, this basket had no apples in it. And this is going to give you exactly what you expect, right? The first basket, there are oranges and gooseberries. There are no apples in this bag. In the second basket, there are strawberries and tomatoes. There are no apples in this bag. And in this last one, we definitely know that there are apples in it because it printed, how do you like them apples? So this else statement, sometimes useful when you have a break condition and you want to do some kind of action after the fact if you didn't have a break. So just kind of a, I would say, fringe tidbit here. Then here there is a very involved kind of take home example that you can do. You can read this later. It's about basically proteomics calculations, and very nicely combines a lot of the concepts taught in this lecture up until this point. So when you have a chance, try and implement this for yourself. The last bit I'm going to talk about here are while loops. So while loops work like this. We have our while, and then we have some kind of Boolean expression. Remember, Boolean means truth, false statements. And then afterward, we have some statements, some code that's going to run basically if this expression is true. And this loop will continue as long as this Boolean expression remains true. While loops don't have an else statement because they don't have a defined, actually, do they? I don't know. I don't think they do. But if anybody figures that out, put it in the chat. Yeah, and once this Boolean expression is false, the loop will exit, right? So here's a simple example. Let's say we initialize count at 0, and then while count is smaller than 5, we're going to print the current count, and then we're going to count plus equals to 1, and then we're going to print the final count, right? And so, as you can see, this this loop runs as long as this count is smaller than 5, because we said we get this print current count for all the numbers from 0 to 4. And then for the 5, this loop doesn't even run anymore. And then we, once this loop is run, we get to this final print statement which says final count. Now you may ask, well, why do we have two kinds of loops? Can't you just have, can't you just use for loops, while loops as for loops? And that's actually how a lot of other languages go about it. Many other languages basically mostly use these while loops and have iterate over, iterate some over collections by saying, oh, this collection is this long, and then have some index variable that they keep track of. We don't have to do that in Python, and most higher level languages, you don't have to do that. So for loops require us to know in advance the number of iterations we want to do, which can be useful if we have, as we said, some kind of collection, some kind of sequential data type. While loops will loop until a condition is met. So an example is, well, if we want to find the largest number in a list of numbers, probably want to do a for loop because we have to go through all numbers once to find the largest number. So we know how many iterations we have to do. If we don't know how long, if we want to run a simulation until a certain kind of mean squared error is achieved, we'll use a while loop. Because yeah, we could just set the for loop to a really large number and break it if we reach the certain mean squared error. But really, kind of stylistically, this is more complete and kind of more beautiful way to solve the problem. It is possible to create infinite loops with a while loop. And I'm going to demonstrate this here real quick. Please don't try this at home, kids. This happens basically if this condition here at the top is never false, right? So let's say we're initializing I at 0. Let's say I forgot to add some incrementation of I in this loop. And now I'm going to say while I is larger than 5, smaller than 5, print I. And this is just going to print I until the cows come home. And so we're going to stop this nonsense. And it's actually going to tell us here at the bottom, oh, it didn't run long enough. Usually, oh yeah, here it'll say output was trimmed for performance reasons. Yeah, which is why you don't want to do this. So let's just clear that output real quick. And so normally if we intentionally want to make an, an infinite loop, we use a while true, because that way it's immediately visible from looking at the code that this is intended to run infinitely or until break is called sometimes in somewhere within the loop. Right? This pattern is useful because it will ensure the code in the while loop is run at least once. That is correct. And there will always need to be a condition to break out of the loop, usually. 99.9999% of the time you want to have a condition to break out of the loop. I actually just recently, and some of you in the audience might know this, wrote a program that has intentionally an infinite loop in it. And what it does is it sends at 9 a.m. in the morning an email to all of our folks in one of the testing labs to check on their health status. So that some of our administrators don't have to get up every morning and write an email to everyone at 9. So that might be a reason why you want to have an infinite loop, or if you have some web server, you might want to have an infinite loop, right? You can always kill the program and then the program stops. But anyways, that's that. Most of the time you want to have some way to break out of the loop. But sometimes you just want to have something running on the side forever until you kill the program. And so if you do have a if you do have this break pattern, you would write while true, then your statements, and then maybe if some condition break. Now you could say, well, you could write this condition into, you could say you could write this condition just into the while loop here, right? Maybe this condition depends on these statements within the while loop, or maybe you have multiple different conditions that each individually can break the loop, and that depend on different things. And so then it's easier to put this break statement in the while loop as opposed to putting this condition in the top of the while loop, right? And so here, for example, we're trying to get user inputs, and we don't know how many inputs this user is going to add. So we're going to say user input equals input of enter a point xy. So we're going to enter a point xy, 1, 2, and 3, 4. Oh, and it's going to ask us for another one, 4, 5. It's going to keep asking us. And then we have this check, if not user input. So input returns a string by default. And this is another thing that's kind of standard Python practice. If you have an empty string or an integer that is 0, or an empty list, or an empty set, or an empty dictionary, those will always return false in Python. So if you call not on them, they will return false. And so if there's no user input, then break the loop. So if we give it just nothing, then it breaks this loop. And then in the end, at the end of this loop, it'll always append this user input to your points, and then in the end, we're just printing all the points we've collected. Here's another kind of just quick FYI. Oh, we're almost done, and I'm almost exactly on time. This is totally by coincidence, not by me actually planning to be on time. There are some other resources for debugging here. If you like the debugging bit earlier, this is a quick way to kind of look at your code and see which parts are working how. And there's this IPDB library, which you can install by using pip install IPDB. I don't know if we're going to use it in this course specifically, but if you want to use it for yourself, this is a nice tool. It's basically going to use the standard Python debugger, which is PDB, which it comes with your Python install, but is going to open it in what's called the IPython shell. This is basically, that's what Jupyter notebooks are using under the hood. They're using the IPython shell. That's why they used to be called IPython notebooks. So you have syntax highlighting and tab completion and all that jazz within your debugger. That's quite a lot nicer than what we had before. And there are some resources here you can click on. Yeah, we're almost at the end here. 2 more data structures you can read up on until next time, if you like. Sets and the collections library. We talked about 2 things from the collections library today, meaning the default dict and the counter. There are some other useful tidbits in there, like name tuple, for example, order dict, although order dict is kind of obsolete now. Yeah, take a look at the collections library. I think, oh yeah, somebody already posted the link in the chat, hopefully. You can also just Google Python 3 collections library. And here a little bit about sets in the last minute that we have. Sets they look like dictionaries, except there's no colons here, right? They look kind of like a hybrid between lists and dictionaries. So they have these curly braces and then just different items separated by commas. And a set can have every item only once. So when we're constructing the set, we're giving it 1, 2, and blah, blah. But in the end, there's going to be only one in the set. And sets are great for, so set means set in the sense of mathematical set. They're great for quickly finding overlaps or differences between different collections of numbers or other things. And so they work similarly to dictionaries. You only want to use immutable objects in these sets. So you can't make a set. You can't make a set that has a list in it. It'll tell you unhashable type lists. It'll yell at you. So you don't want to do that. And so read up on what sets can do. As I said, it's mostly for example, if you have some data set and it has some columns and you want to see, for example, are the columns the same between these two data sets, between these two data frames, right? Something like that is very useful for that. And they're very fast. They're very fast as compared to if you were trying to do the same thing with lists yourself. And one quick tidbit, you can add to sets and so on, and you can remove from sets. So sometimes it's useful to make an empty set and just keep adding to it. Although usually the most performant is when you give it everything at the same time. But sometimes you want to make an empty set. You'll have to call set like this. This does not give you an empty set. This gives you an empty dictionary. So keep that in mind if you ever want to make an empty set. You need to call it like this. Yeah, that's about it, I would say, for today. Thank you, everyone. Thank you, Mark, for these largely unaltered IPython notebooks. I did some editing on these, but this is almost all Mark. So thank you very much, Mark.